to our YouTube channel, Becoming a ROS Developer here at The Construct. My name is Rodrigo, and today we have one of our students, Mike, who has completed a project for one of our courses, ROS2 Basics in Python, in 5 days. And at the end of the project, at the end of the course, the students have to complete a project that has to work on a real robot here at The Construct. So that's what we're going to be seeing today. Hello, Mike. How are you doing?
Hello. Thank you. I'm good. How are you?
I'm good, thank you. So yes, whenever you want, you can start sharing your screen and show us what you've done with your project.
Splendid. So I'll make the robot do the talking.
Ah, nice.
So here we can see the environment.
Yes, I can see your screen and the robot.
Yeah. So as promised, I will launch my program, and I'm trying to check if, yeah, it's looking like running, and I'll try to gloss over the basics. So here we can see that the robot is spinning to face the wall, as indicated by the last line, face forward. And I'm hoping that so I was afraid that the signs will mess up the logic, but it supposedly is all right. So I will have a presentation later on going into more of the details. But as the alignment has completed, we can see that the
robot starts going around.
is doing his main objective of completing a full-on circle by following the wall. So as it follows, we can see a real-time feedback of the data, which consists of two parts. Basically, the one is tracking its origin position, just to know when the full circle has been done. And the other is calculating the current total distance traveled, which is being done every second. So as the robot moves on, we can hope that the distance to origins gets closer to, smaller.
So that's around the time. So it's like a radius of the area where the robot first started.
It's keeping track of the original position and just, as I imagine, drawing a line to the current position. And it's trying to check whether that distance is lower than 15 centimeters. So yeah, the robot has successfully completed its task, and it is indicated by sharing me all the knowledge of his travels, meaning that every point that he has tracked.
So it's the path that it took.
Yeah. So I guess I can move on.
Yes, awesome. Now that
presentation.
We see a great function. Yes. Why don't you
can go into detail how I accomplished this? So present. Yeah. Is everything seen?
Yes, I can see your presentation now.
Okay, perfect. So this course project is a really good way to apply your knowledge. So I will try to keep note of my learned knowledge and what I try to apply. So as we can see, we have an environment, and this is what we get. In simplest terms, a table with 4 walls. And if you look closely at the top left, we can see a robot. And as I understand, this is a burger version, a Turtlebot burger version with the sensors that will be most, we will be using, and relevant for us is 360 LiDAR sensors and 2 move wheels and some odometry magic. I call it magic because it's really fascinating to me. how it can keep track of its orientation in space just with moving. And
Yeah.
I don't really know I haven't had time to get too deep into it. So the goal is to achieve a wall following behavior, which consists of the main following loop, just going in this circular motion. Its starting point, which is described by finding and aligning to its perfect position, as we could say, and some kind of end goal. So keeping track where it started and stopping at that point. So in that order, we have those tasks: task 1, task 2, and task 3. So starting with the task 1, this wall following loop, here we learned about publishers and subscribers, which corresponds to gathering data and publishing some action, as I can say, in the terms of the robot movement and logic in between. So the logic is dependent on the wall being on the right side, and we gather data from the laser, which corresponds to the robot's right side. So based on that, we can kind of imagine these three zones. And in these three zones, we just attach the behavior of going straight, left, well, slightly to the left or slightly to the right. And here we can see that logic represented by code. But as we can see in the front, we have some unexpected situation for this logic, which means we have a wall just right in front of us. So we need some additional layers of having a sharp turn to the left. And here we can see that the logic is quite similar, just now using the laser that is pointed to the front. Well, I could say the laser index. And just as a special note, I added this red arrow, which makes the robot go backwards, because I found in some cases where I got stuck, mostly in the simulation, the robot would be on its track if he just moved a little bit back, where he found himself like rammed up to the wall. And all this logic relied on being inside of a loop. And here we learned of a object called timer, where with the help of it, we could have this logic and simultaneously collect laser data. So what kind of difficulty we had? So as I mentioned, the laser corresponding to the robot right has some kind of a, well, I call it flaw, but this logic only relies on this one singular data. And in this situation, we can see like on the right side where the robot is moving in towards the wall, but the laser is kind of looking like the wall is further apart, where it's imagining that, well, I need to go closer to the wall. And we can see in the reality, it's not beneficial for us to go toward the wall. We will just crash into it. So I call this difficulty in quotations because I unknowingly fixed it by not taking into account the laser index difference between simulation and reality. So in simulation, when I use the laser index, which is like the utmost right position, in reality, it turns out to be luckily on the same right side, but slightly more towards the front. So what happens is the robot is actually referencing the closer part of the wall. Well, to put in practice, here he can see that the wall is much more further away, so he can, well, basically this see wall much more quicker than it actually happens. And in this same situation where it's getting close to the wall, it sees that it's getting close to the wall and then corrects itself. And then we have the next task. It's the wall finding and aligning, as I called it. Here we learned about another concept called service, where the robot's one program called the node asks for another node to complete some kind of a task and then receive a response. So the logic for this service is split into 3 parts. Here I learned about a style of, I guess, state machines. So I just reference them as states. So the first state is to align the robot to the wall. And this is being done by having this yellow line, which represents the shortest index that the laser can see. And trying to match that with the robot front. Then it uses the same shortest index distance to align it to 30 centimeters, and then the same logic as in the front, but now aligning to the right. And this is represented in code. This is the mode that gets repeated until some kind of condition is met. So in this case, alignment. I repeat this code. I then at the end change the mode to distance align, then really similar logic, and repeat it. Then I switch modes to face right. And then here I have this little bigger picture because the right index does not match in the simulation and then in reality. So it just looks a little bit bigger because I found the easiest way just to check for simulation and then change some variables. And at the end of it, I just set the mode to align, and this is all being done inside a while loop. And this is a key moment because this is where I stumble into some difficulties. So what the first difficulty could be is my stubbornness to just go by the book. What I mean by that is when I did the first part, I saw a message that I should then try to apply this part, the wall following, and then I did the services. I just saw you should finish part 2, and I never looked further. And this was a real stubborn mistake for me because I really needed to understand the callbacks and multi-threading, meaning, as I mentioned before, when I was doing this state machine inside a while loop, it was blocking my data from the laser, and I could not get updated data for the laser, which my logic relied on. So I spent a lot of time, and I'm really grateful for the forum because this is where I found all of my needed answers. I didn't really need to look that far. And I then repeated those in the later sections. And another big part was the strange behavior where I saw my robot kind of lagging behind. I'm not really so sure about if I understood perfectly what was happening, but my this difficulty to understand made me solve another set of problems, like having not to rely on one index and having a range of indexes for the laser, then checking that the simulation and real robots don't match in the laser index range. And the spinning just really came down to having one sleep period of 0.1 seconds, which my hypothesis is my robot was kind of lagging behind because it was receiving a lot of messages and it was not keeping up with the execution. Like it would still be trying to process the spinning messages when the program was already shooting or spewing the messages of moving forward, and then it would kind of lag behind and mess up my logic. So this kind of worked for me. So I guess it's something along those lines. And the final task, which was having an endpoint, and this was being done by learning and using an action server. and it's really similar to the service, but here we can provide some feedback, which is also called that way in programming, in the logic of what is happening while our task or action is being done. So the logic here is once the action server is called upon, we reference a point in space, which I will represent as this little point. Then along the path, every second we reference another point, and we start to add them up. Also, yeah, so in code it looks like that. And we then add those distances just using Pythagoras, I think. Well, the method is not the main topic. And then we always try to check if we are close to the starting origin distance. And here I took the privilege of broadening the range. I mean, when at the time when I was doing the distance was recommended to be about 5 centimeters, but I found that reality is often disappointing and not so precise. Just to rely on this one distance, so I just extended it a little more, and my program was running perfectly. So just at the end, the requirements was to share all the acquired data. So that's just a part of sending the results, which are represented like this. And the difficulties. So I just mentioned this one. It's the increasing the allowed error in distance. And the more tricky part was how does the robot know that it did a full circle? Because when I start to question, okay, how far is it from the starting distance? Well, we are at the starting distance, just at the start of the loop. So I need to make sure that the robot already has done a loop, and then it starts to check. So what I did was check not only if the distance condition is met, but also check for if the actual distance is getting smaller, meaning that we are getting closer in, not being further apart. So if the robot is moving like to the left and it's this is the reference position, I can have compared the distances like the past one. I just have to have another variable which stores the past distance. And if I'm closing in, always the distance passed should be bigger than the current one. And vice versa, if I'm going away, then the logic will be inverted. And if we combine all the logic, we have this RQT graph, as I believe it's called.
Yes, yes.
Yeah, it was a really good program to check out how it all connects and visualize if it's all set up, because it's actually looking at the real robot state. But here, what is missing is the first calling of the action or of the service.
Right.
Because here we can see that laser, it's giving the data to the wall finding service and the wall following loop. The third action doesn't need this data. And yeah, so I said the missing parts are the, as I said, the calls. So
Right,
what
gets
starts
executed.
those actions? Yeah, I don't really know how to implement them into those into that program, so I just referenced them like this.
Okay.
And I think, yeah, that's it. That's what I got. Thank you for your time.
Great, great. Nice, very, very nice. Do you mind stopping sharing your screen so we can
Yeah,
sort of
yeah,
uh, look at you now that we see the
yeah.
project? All right, great. congratulations, Mike. It's a really nice
Thank you.
project, really clear. I just
I
want to
really
say
enjoyed it.
uh, thank you. So I just want to say that I always appreciate, and for the audience and for everyone else that's watching, very clear presentation, a very illustrative of clearly what the goal of your project was, what the tasks you did, and the challenges you made. You made it so clear with the images of the real robot. So really, really nicely done there. Uh, so congratulations. I want to ask you a couple of things just to
Yeah.
wrap up here. Actually, I want to make a comment first. You talked about your stubbornness in this service part that instructed you to go to the project at that point, right? Before going into
Yeah, yeah,
multi-threading
yeah.
and callbacks and callback groups. So I wanted to say that is not a mistake from your part. I understand that. And thank you for bringing this to our attention. What we're going to do is just simply put that message at the end of the sixth unit, which
Oh,
would be
yeah,
which
that
would
was
take care
simpler.
of these things. I understand that, and um, that's a good point that you're making there. One question I did have though is that it has to do with the you. I really liked how you put the sections of in the like real lab of what the robot would be doing, and then you included one part when it's approaching the wall. It's less than 50 centimeters, less than 30, do something, and then you mentioned less than 5. Back up and sort of turn towards the other way.
Yeah, yeah, yeah.
And you mentioned, can you go into a little more detail? Is this on the simulation you mentioned that what was happening? And why do you think it would get ahead so it has to do that correct and move?
So in the simulation, I was using like the most right index. So meaning
Oh,
that I have a really sharp turns, and I would just kind of wiggle, and then wiggle myself into the wall, or
right. And that's
maybe
why it didn't happen in the real robot when you explained, right?
in the real robot. What happened was the corresponding index of truly to the right one was actually on the more forward-facing right.
Further
Well, I
ahead,
could
yeah.
say that. And here, when the robot was leaning into towards the wall, he would see that the wall is closing in because he would kind of be looking more straight and to the right.
Right.
Because if it was totally to the right and I was facing the wall, I would see that I have very much distance.
Right,
Like,
right. So you would run into the same situation, but because of this lighter difference, it wouldn't happen in the real robot. Although I have a feeling that once you changed, you talked about how you were taking just one value, and then you changed
yeah,
to taking a range. I assume if you make that range big enough, I would assume that that problem would be somewhat mitigated, right? That's fair to
yeah,
assume.
yeah. Well, that's the magical part. There's
Mm-hmm.
all kinds of solutions,
Right, right, right.
and
Yeah.
I really like leaving the first tries inside my presentation because it just shows that this works. There can be other ways. And it's kind
Yeah.
of like evolving because
Yeah,
I
of
first
course.
had like just little driving back. Well, if I did it again, I would totally make it even better.
Right, right.
I hope so. Yeah.
No, I understand, and I agree. There's many, many ways to solve this. And just one last
Yes.
thing that you mentioned that I want to just tell you is that you are actually the second person that mentions the increment of 5 centimeters to complete that lab to 15, because things are gonna happen in the real world that 5 centimeter
Yeah. Yeah.
radius is harder to achieve. So what we're going to do is just increase that limit to 15, because at the end of the day, that part is not what our project is looking for,
Yeah.
and we
Yeah.
don't want students to focus on the wrong things. I'd say so. That's another comment that I thought was very good point on your part. But other than that, Mike, that was a really, really nice presentation. So I just want to congratulate you
Thank you.
again. Yeah. And for us here, I think that will be it for us, you guys. So anyone else that is watching, you can do here what Mike is doing in order to get one of our certificates of learning after taking one of our courses. So I encourage you, if you are in our platform, to go ahead and take the leap to present one of our real robot projects and yeah, showcase what you've learned in our courses. Thank you again, Mike, and we'll see you for the next one.
Bye.
All right, guys. Bye-bye, everyone. Okay, cool. We're done. All right.